In this demo, we show how P4 programmable switches can be used for real-time robot control. In this demo, we use the idea of in-network computing, which means that we move computations from servers to the network, actually to programmable network devices, network switches. Programmable switches are not only packet forwarding elements nowadays, but they can also perform traditional computations. They ensure high throughput and ultra-low latency, and of course we have to face lots of limitations, including the pipeline computing model, limited number of stages, and limited memory capacity. This slide illustrates the system design of our in-network real-time robot control scenario. We assume that we have silly robots, which means that they are a set of actuators with UDP-based communication. We have a P4 switch in the middle, which is responsible for calculating the velocity vectors, and it sends commands to the robots periodically. And we also have an industrial controller, which calculates the trajectories and loads the trajectories to the P4 switch. Trajectory in the P4 switch is represented by a sequence of robot states, where a robot state can be imagined as a snapshot taken at a given point of time. The transition between two robot states are calculated and performed by the P4 switch. Let's see our demo. This slide illustrates our demo setup. It consists of a robotic operating system, ROS, a P4 switch based on Barefoot Tofino, and a UR robot. First, we have to start the switch, which means that we have to execute the switch daemon, and we have to load the appropriate P4 program. Then we have to configure the ports of the switch. After that, we also have a control plane program. And the control plane is responsible for filling the tables of the data plane. It was implemented on top of Barefoot Runtime API. We also implemented a Python CLI, which can manage the control plane. Through the CLI, we can set the different parameters of the underlying PID controller. This PID controller is actually implemented by the P4 program. We also have a trajectory proxy, which is responsible for translating the messages coming from the robotic operating system to messages processed by the control plane. It means some kind of transformation between the trajectory representations. We also implemented a ForkProxy for the UR robot. It can be loaded to the robot's firmware. It's basically a plugin. And it implements a UDP-based communication. And then we are ready. So first we have to plan a trajectory. Then we send the trajectory to the trajectory proxy and load it to the control plane, and the control plane will fill the tables of the data plane. Then the UR robot will send status messages to the P4 switch, and the P4 switch will generate velocity commands and send them back to the robot immediately. So here we start the robotic operating system. It plans the trajectory and forward it to the trajectory proxy control plane in the P4 switch. And here you can see the 3G object of the robot arm, and you can see how smoothly it operates. So in this scenario, we loaded the entire trajectory to the P4 switch, and basically the P4 switch solely controls the movement of the different joints. As mentioned, the trajectory is represented as a sequence of trajectory points. It can be imagined as a linked list. And we can also add higher priority links, and in this way we can change the original path. So it's good for changing between alternative trajectories, for example. So where we can use that? The first example is that in industrial scenarios we often have to implement a repetitive task, and it means that at the end of the trajectory we have to move back to the initial point and continue the operation from that point again. So here you can see a welding example without the edges of an object, and you can see here without the two edges, and then we change the object and move back to the initial position and continue the operation again. We can also use a higher priority link to stop the procedure. And by removing this extra link, we can continue the operation from that point. Here you can see an example. We start the operation and we stop here. And after removing the extra link, we can continue the operation. And finally, we can also use this extra link to change the direction of the movement. So for example, at some point we can decide to move back on the path. So here you can see the welding example. So here at this point, instead of moving to the upper edge, the robot arm turns back and moves along the bottom edge. So what we have now, we fully integrated our P4-based velocity control with the robotic operating system. And from the robotic operating system's point of view, it totally transparent whether we use a direct control of the robot arm or we use our P4-based implementation in the middle. It also means that we can use all the different tools on top of the robotic operating system without any modifications. And thank you.